In this lesson, we are going to look at how energy is related to heat and enthalpy. So, first of all, we know that energy is often measured in joule, okay? So let's look at heat and enthalpy. First of all, enthalpy, basically all substance has a certain enthalpy. What is it? It's basically the sum of the system internal energy. So every substance or every matter has some sort of internal enthalpy. That's because they have certain amount of energy in it. Now, of course, energy is measured in joule, represented by the letter J. Now, what about heat? Well, heat represented by Q, where enthalpy represented by H, which makes sense, okay? Think of enthalpy as like the heat content of a system. Now, where heat is the energy being transferred, so this energy is moving from one place to another place. So when a substance is gaining energy, that energy that being transferred in is considered as, and when a substance is giving up energy, that energy is also known as heat. So again, heat is the energy that transfers from one object to another object at constant pressure. That happens to be an open environment. There is no control of the pressure. So one thing we need to keep in mind that energy naturally will always flow. That means it will always go from one place to another place. Specifically, it will always flow from a system of higher temperature to a system of warmer temperature. Basically saying that if you have a hot object in contact with another cold object, that energy in the hot object will go to the cold object. Eventually, both systems have the same temperature. Okay? So it's always flow from high temperature to lower temperature. Now, notice how we say enthalpy is the sum of internal energy. But what happened to internal energy change? We have delta H. We call it change in enthalpy, okay? So in a way, isn't this the energy being transferred, either releasing or gained? And that's the reason why we have delta, which is delta. This is the symbol for delta right here. And deltas usually represent change. So the change in enthalpy of a system equal to heat. That is the energy being transferred from one place to another place. Now Q, which is heat, is equal to this equation. Q is equal to mass times specific heat times delta T. And again, delta T is the change, right? When we look at change, what are we really looking at? The change is always relative in terms of final. In this case, we have delta T, that's T final minus T initial. So every time you see delta T, always think of final minus initial. And of course, I further describe them here. Q again is the quantity of heat, the energy being transferred, and is measured in joules or calories. Well, M is mass in grams. And of course, delta T is T final minus T initial. And lastly, this is where the most important piece of all is the specific heat capacity. Why is it important? That is because it tells you what unit M need to be. Notice how we have G, that tells you gram. Notice how J, that tells you your Q must be in joule. And look at the C. So what is heat capacity and how is it different from specific heat capacity? Well, first of all, heat capacity is the energy required to raise 1 degree of Celsius. Okay? So how much energy? That's why we have joule over Celsius. How much energy do I need to raise 1 degree Celsius? Whereas specific, think of the term specific. That's because different substances have different heat capacity. Well, if we look at the unit of specific heat capacity, we have energy, right? And how it's being divided by gram and Celsius. Basically saying that different object has different heat capacity. That's because it's required different amount of energy to raise 1 degree of Celsius for that 1 grams. So keep that in mind, is per 1 gram of the substance. That's very important, okay? So that's specific heat capacity. Now, if we look at the list of specific heat capacity, what does it tell you? Of course, the one with the lower J right here is the one with the lower J right here. Okay? So that would require very little energy to change the temperature. So keep that in mind. And where the one that has very high specific heat capacity, it would require a lot of energy. For instance, metals have very low specific heat capacity. That's why we use metals in our cookwares, so that way it easily increase the temperature. Isn't that nice? So we can cook faster. You already know that the amount of energy in this universe is constant. What does that mean? That energy is neither create nor destroy, just like matter neither create nor destroy. Okay, so if that's the case, the amount of energy is being lost should be equal to the amount of energy being gained. That's why we have negative Q equal to positive Q. So that's the concept behind it. And one of the most common equipment that we use to determine how much energy is being released is a coffee cup. Think of the word coffee, okay? We use a coffee cup. And a coffee cup, if you ever hold a coffee cup before, it is very well insulated. So that means all the heat that's being released by the system in this container, it will be changing the temperature. So we can measure the change in T, and once we get the change in T, we can actually solve for specific variable in the equation. So we're going to look at those more specifically. So again, know that we are using a coffee cup calorimeter. Okay, calorimeter. Say that again. Calorimeter. Now let's try one problem together. How about that? How many joules are needed to warm 45 grams of water from 30 degrees Celsius to 75 degrees Celsius? The specific heat water is 4.184 joule per gram Celsius. Okay, so if we read this problem, we know that we are looking for joules, so that'll be Q. Easy, isn't it? And we know that that would be your mass because it's a gram right there, and of course is in the right unit as well. And then we are going from T, this is your TI, which is your initial, and we're going to TF. So we do that, we can just solve. Now let's use the equation. We know that Q equal to MC delta T. And the one way you can remember this is MCAT. Think of the delta, look like the letter A, isn't it? So we call this MCAT. Q equal to MCAT. Okay? So in this case, your mass is 45.0. And notice how I don't put the unit there. Okay? And my specific heat capacity is 4.184. Again, I did not put the unit there. That way it doesn't confuse. And then the last thing we have is delta T, which is T final minus T initial. In this case, it is, we know exactly what it is already. The T final is 75.0, and the T initial is 30.0. And then all we have to do is just plug this into the calculator. Isn't that easy? So if you plug this into your calculator, what you have is 8470. And we want to keep 3 sig fig because our answer. So what is the unit for Q again? Of course, it's joule. And there you go, that is your answer. Now in this case, what happened to the system? Is it gaining or losing energy? Well, let's look at this water. It's starting from very cold temperature of 30 degrees and get really hot to 75. So the only way that's possible is gaining energy. Okay, let's try another problem. A sample of lead, its specific heat capacity, my bad, okay, is 0.138 joule per gram in Celsius. Release 1200 or 1200 joules when it's cooled from 93 degrees Celsius to 30 degrees Celsius. What is the mass of this sample of lead? So again, Q equal to MCAT. Okay, and we know a Q in this case is down right there, which is 1200. Then do we know our M? Our M in this case is what? We don't know. We are looking for the mass, so M right there. And we know the specific heat is right there, so which is 0.138. And do we know our delta T? Of course, from final minus initial. In this case, the final is 30. and 93. Okay? Isn't that easy? And of course we know that this is losing. Notice how this system is losing energy. And how do we know? It's starting from a very high temperature to a very low temperature. So this key over here, there's one last tricky part. So that when it loses energy, it's actually a negative. So we have a negative 1200 joules. So how is that going to affect our answer? Of course, if we do the math behind it, look at this number. We take 30 minus 93, that gives us 63, specifically negative 63, isn't it? So if we plug this into a calculator, of course, we have negative 63 times 0.138. And notice how we have a negative answer, okay? So notice how when we plug this in, notice how when we calculate it, we have a negative answer. So we have m times negative 8.69, okay? Let's keep 3 decimal places for now. And that's equal to negative 1200. And what is m going to be? Of course, we're going to divide both of this side by negative 0.694. Answer. So your m is going to be 138.03. And for this case, we're not going to care about sig fig that much. Just skip that right now. I just like to keep this 2 decimal places. So what's the unit for mass going to be? Of course, it's going to be grams. And specifically what chemical? Of course, it can be lead, Pb. So your mass is equal to 138.03 grams of Pb.